Hi everyone. Today we're going to focus on drawing electric circuit diagrams and doing some resistance problems. So to start, if you could read page 701 to 703 in your textbook, you'll get a better understanding of electric circuits for today. So after your reading, you should have noticed these definitions throughout your reading, so just some important ones to note. Also, it'd be a good idea to copy down these symbols beside each definition, okay? So we have open circuit, which means there is a break, perhaps an open switch somewhere in the circuit that prevents current from flowing. We have closed circuit, which means that all connections are complete and current can flow. We have ammeter, and that's a device that measures the electric current through a circuit element connected in series with the circuit element. We have a voltmeter, and that's a device that measures the electric potential difference, so voltage, across the circuit element, and that's connected in parallel with the circuit element. Then we have the important one for today, which is resistance, and that's a circuit element that resists the flow of current in a circuit. It's measured in ohms, so you will get used to drawing this in ohm. And resistance in a circuit is affected by four things. So it's affected by temperature, so resistance increases as temperature increases. Length, resistance increases proportionally with length. So as resistance increases, length increases. We have area. So the smaller the cross-sectional area, the bigger the resistance. So the resistance is inversely proportional to area. On the side here, we have just a reminder of the formulas to calculate area for a circle and a rectangle. Also remember radius is the diameter divided by 2. And then we have the fourth one, which is material. So different materials have different resistances to current flow, called resistivity. And that's noted as rho, the Greek symbol rho. It looks like a P. So with all that information, we can calculate resistance. So this formula should go on your formula sheet. So resistance equals the resistivity times the length, and then divided by the area. Okay, so we're going to use that formula later today. Before we get to that, if we can practice drawing circuit diagrams. So we're given this diagram and we want to move it into a circuit diagram, which is given to you over here. Okay, when you're drawing circuit diagrams, I normally start at the power supply or the battery in this case, right? So that's where I start, but it's up to you where you start. When you're drawing the power supply or the battery, the long line is the positive end, so the anode, and then the shorter is the negative end, which is the cathode. Okay, and then if you can show conventional current and electron flow with arrows, that would be good as well. So you will also be given a sheet of symbols to draw for circuit diagrams, and it is on the classroom. So if you want some more practice, you can go on the Colorado Institute, the PhET simulator, to practice drawing circuit diagrams, and there's a link for that on the classroom. So on page 702, there's a conceptual problem that is really neat to look into. So in one of the circuits shown here, the arrows represent conventional current. In another, the arrows represent electron flow. One circuit is drawn incorrectly. Neither conventional current nor electron flow could take the directions indicated by the arrows. So analyze the circuits and determine which illustrates conventional current, electron flow, and neither. Explain your reasoning. So let's take this first one. So as you're looking at A, I usually start at the power supply or start at the battery. So then find the arrow that comes out of it. So this way, the red arrow is pointing down, so out of the cathode. So when it's coming out of the cathodes, that's electron flow, right? The way the electrons move. And the arrows keep pointing, they go through the resistance, and they keep pointing us all the way towards the positive end, okay? Now, let's go to B. So again, let's start here. Let's start at the battery, and so we're coming out of the positive end, so it looks like it's going to be current. Oh, we keep going through the resistance, all the way, and it changes direction. So what if we start from the negative end? But it still goes backwards. So this is neither, right? It's neither conventional current nor electron flow. And then C, with process of elimination, if we start at here, the battery, we come from the positive end. So that's conventional current, and all our arrows point towards here. Okay? This one at the bottom here, if you want to give it a try, you can, but not really important at the moment. Okay? All right, so now we have a sample problem to get ready for some book questions. So on page 707, there's this model problem. So using resistivity. So calculate the resistance of a 15-meter length of wire copper at 20 degrees Celsius that has a diameter of 0.050 centimeters. So write out what's given. So when you're trying to find resistivity, so the row on page 706 in your textbook, it gives the resistivity of some conductor metals. So you will see copper there. It says copper wire, and it gives you this constant, so 1.7 times 10 to the negative 8 ohms times meters. We have our length, 15 meters. It gives us diameter. So it's in centimeters, change it to meters. So then we know that the radius is half of that. And we're trying to find resistance. And then the next thing we need to find is area. So this is a circle, like a wire is a circle, right? So we're trying to find the cross-sectional area. So we use pi r squared. So we take pi times by the radius squared, we get this answer. Then we're going to move it into that formula that we looked at earlier. So resistance equals resistivity times length divided by area. So you just plug it all in, and all our units cancel to give us ohms, and that's what resistance is measured in. So 1.3 ohms is our answer. So this is a slide to give a quick explanation for cross-sectional area and resistance, and in some real-world applications. So we're going to look at wire gauge, and that's a term people use to measure the diameter of wire, but it's good to note that the wire gauge is not actually the measurement of the diameter. It's just a gauge, right? So it determines the amount of electric current the wire can safely carry. And the smaller the gauge, so the smaller the number, the thicker or larger diameter of that wire. Okay, so in a house, the wires in the walls that carry power to outlets is usually 14 gauge. And that's relatively thick. This has a larger cross-sectional area, which lowers the resistance. And when you compare that to an extension cord, which are usually thinner, and that's at 18 gauge, and that has a smaller diameter and has a more resistance because it doesn't need as much voltage to run the appliances like a toaster. Okay, and then this little chart down here shows the length and gauges of some extension cords, because as you know, there's different sizes of extension cords. Like if you needed a thicker to carry more voltage, there are those, but usually we see thin extension cords because it's running like a little appliance or a little lamp or something like that. But this just shows some of the extension cords and how it changes the amps the wires can carry. Okay. So now we have some questions to do. So number 16 to 20 on page 708. So give those a try. Let me know if you have any questions. Come to the Google Meet or email me at any time. Okay. And like I said, go on the PhET simulator just to check it out. We will be using it in the next couple days. So it might be nice to be a little familiar with it. But other than that, have a great day, and I'll talk to you soon. Bye.